Howdy, and welcome to the auxiliary lecture on wind turbines. So wind turbines are very interesting to talk about for two reasons. One, of course, they're a thermodynamic device, even though you may not have attached the word thermodynamics to a wind turbine system before. But secondly, of course, they're very popular in today's discussions. Wind energy is cited as one of the more popular ways to use alternative energy. And of course, the basic idea of a wind turbine is to take the kinetic energy of wind that's flowing in a directed fashion and cause this kinetic energy to be transferred into rotating shaft energy. That's what the blades of the wind turbine do. And then this rotating shaft energy is transferred into a generator. And a generator, of course, takes shaft energy and converts that shaft energy or shaft work into electrical energy or electrical work. Of course, wind turbine systems, or windmills to be more precise, are not new technology by any stretch of the imagination. We've been using wind energy for a long time, sailing across oceans with sails and using wind energy to drive water pumps and turn food mills to grind grains and such. But in terms of actually using wind energy for the direct generation of electricity, that's a more modern activity, of course, as electricity itself is more of a modern activity. So the diagram that I have shown here is basically a sketch of how a wind turbine system works. And of course, you can see the wind energy flowing in to our wind tunnel. And so these two dashed lines that you see here, these symmetric dashed lines, represent what is called the wind tunnel, and I'll talk more about the wind tunnel in just a moment. But the wind energy flows in a directed fashion into our wind tunnel, and that wind energy then flows past our wind blades, and of course the kinetic energy of the wind is transferred now to the blades, and it causes the blades to spin. We now have these spinning blades which are attached to the shaft. And because the blades are spinning and they're attached to the shaft, it's causing the shaft to spin. And so now we have shaft work. So our blades and our shaft are basically serve the function of taking the kinetic energy of the wind and converting it into shaft energy or shaft work. Now that shaft work, of course, can be used to do many different things, as indicated by some examples that I just gave, where you could use that shaft work to drive a water pump that's pulling water from the ground, or to drive a mill that mills grains or does other types of activities. But in the case of a wind turbine electrical generation system, that shaft work is transferred directly into a generator. So this box here represents the electric generator. And of course, the function of a generator is to take shaft work and convert that shaft work into electrical work, or electricity. A generator is just the opposite of a motor, an electric motor. In the case of an electric motor, you supply electricity, and that causes the shaft motor to spin. In this case, we're supplying the shaft work, we're causing, with some other means, the shaft to spin, and the internals of the generator are such that we generate electricity. In fact, the internals of a generator, in terms of windings and electrical wire and stationary magnets and things such as that, are all the same as a motor. An electric motor and an electric generator functionally are designed the same. The primary difference is in the case of a motor, you supply electricity and it causes the shaft to spin. In the case of a generator, you supply the shaft work and electricity is produced. Okay, so I mentioned real quickly that I'd talk more about this wind tunnel, and so I will very quickly. It's not something that we really focus on much in this class of thermodynamics. We're much more interested in the energy relationship of all of this. And this wind tunnel is more of a fluid mechanics relationship. And basically it's just Bernoulli's principle in the sense of you have wind energy that's coming in, and this wind energy has a velocity. And as the wind energy is transferred to the rotating shaft, that causes our wind velocity to decrease because we're now removing energy from the wind. And consequently, because of that decreasing velocity, the flow area indicated by this expanding diameter of the wind tunnel here on both the top and the bottom, increases, right? So you have now a lower velocity, and based on Bernoulli's principle, that corresponds to an increase in the flow area to compensate for the same pressure that's acting on the system. More importantly for our discussion, of course, is that because this rotating blade system is taking energy, is converting the kinetic energy of the wind into shaft energy, our inlet velocity is greater than our outlet velocity. Now, the other thing that you'll notice that I have written on this diagram is I say here that, this box, of course, is our turbine generator, and it says that it assumes 100% generator efficiency. We'll talk a little bit more about efficiency toward the end of this auxiliary lecture, but what that really means, just for the sake of the discussion now, is that if we assume 100% generator efficiency, then all of the shaft work going into the generator is being converted completely into electrical work. Okay, so a generator is one such device where we're not limited on how much our efficiency can be, or at least the limit is 100%. Of course, if it were greater than 100%, we'd be violating conservation of energy and actually creating energy. But there's no reason why, ideally, the generator efficiency could be 100%. In other words, it doesn't have to be less than 100%. As is true with some other types of energy conversion that we do, such as thermal energy to work energy in a heat engine. And of course, we'll talk more about that as the semester goes along. Okay, so now what we need to do is we need to take that sketch that we drew, and we need to create what we call a thermodynamic representation of that sketch, and that's what we call our control system. And so what we want to do is we want to understand, first of all, what is our control system? In other words, what is the region in space in which we're doing our analysis on? And then how does that control system interact with its surroundings? Well, it's probably fairly straightforward to see that our control system, our thermodynamic control system, in the case of a windmill, are the blades plus the generator. So because we're defining that as our control system, so you can see here that I created our box, which we call the control system, and I say in parentheses here that the system includes the blades and the generator. Okay, so what that means is that now the way that our system is interacting with the surroundings is we have an energy flow rate in, well, that would be our wind energy coming in, the wind velocity entering the control system, and we have an energy flow out, that would be our wind energy or our wind velocity leaving, the kinetic energy of the wind leaving the control system. And then, of course, we're generating electricity. So we have electrical power, which is leaving our control system. Now, let's just, for the sake of a brief discussion, say that we, instead of defining our control system as being blades plus the generator, we instead defined our system as just being the generator. Okay. In that case, now we actually wouldn't have flow terms, right? We have no mass flow into the generator and we have no mass flow out of the generator. Instead, what we would have is we would have a work term, shaft power, into the system, which is just our generator, and we would still have our electrical power coming out in the form of electrical power. We could also say that, or imagine a situation where we define our control system as being just the blades, not including the generator. Now, in that case, we would have energy flow in with our kinetic energy of the wind flowing in and kinetic energy of the wind flowing out because wind is passing the blades. But now our work term out of the control system would be the shaft power, not the electrical power. In other words, the shaft power is what goes into the generator. And so the actual output of that system would be shaft power, not electrical power, if our control system were just the blades. But as you can see, we can simplify our analysis by just including the blades and the generator within our control system. Now we no longer need to separate these intermediate work transfer terms out, since that work transfer is occurring internally within the system. And so we don't have to worry about it. It's not crossing the system boundary. These are the only things that are crossing the control system boundary: the kinetic energy in, the kinetic energy out, and the electrical power out. Okay, so now that we have this thermodynamic representation of our system, and we're calling this our control system, we now need to know how we can generate or write our governing equations for our wind turbine system. So the next question to ask is, the first question is, well, how do I represent this control system in mathematical form? And the easiest way to answer that question is to compare this control system to our general thermodynamic system, which I've drawn down here below. So just to remind you, our general thermodynamic system, of course, includes everything that could happen to a thermodynamic control system at this stage of our understanding of thermodynamics. So of course we have our control system, and our control system itself can change with time. In other words, the mass of the control system could change, the energy of the control system could change, and the entropy of the control system could change. Now these three elements, or these three terms of our control system, can change only by virtue of interaction with the surroundings. In other words, we could have energy flow in and mass flow in. We can have energy flow out and mass flow out, and entropy flow out. I apologize. Mass, energy, and entropy can flow in. Mass, energy, and entropy can flow out. We can also transfer energy and entropy into the system with our heat transfer term. And we can exchange only energy with the surroundings with work transfer. Okay? So the only two ways we can transfer, or I should say the only way we can exchange mass with the control system and the surroundings is through mass flow in or mass flow out. The only way that we can exchange entropy between the control system and the surroundings is with entropy flow in or out and with heat transfer. And the only way that we can exchange energy between the system and the surroundings is by having energy flow in along with the mass flow rate or energy flow out. And we can exchange energy through heat transfer with the surroundings, and we can exchange energy through work transfer with the surroundings. Okay, so we can represent these three exchanges, these three interactions between the control system and the surroundings with our general thermodynamic equations. And so we have, of course, three, and as I've mentioned, these three equations are going to be used repeatedly in our study of thermodynamics this semester. We have the change in mass of the control system is just a balance between the mass that flows in and the mass that flows out. This is based on conservation of mass. We have the change in energy of the control system, which is also, the change in energy of the control system is also based on what is called the conservation of energy principle. That is, energy cannot be created nor destroyed. And so the way that we write this is that our energy of the control system, the way the energy of the control system changes, is balanced by energy transfer with the surroundings through heat transfer, and energy transfer with the surroundings through work transfer, energy that's transferred in with a mass flow rate in, and energy that's transferred out with a mass flow rate out. And then, of course, we can quantify the entropy change of the control system with time, and that is done with the following four terms, and that is entropy that's transferred with the surroundings because of heat transfer, entropy that's transferred in from the surroundings with the mass flow rate into the system, entropy that's transferred out of the control system to the surroundings due to mass transfer out of the control system. And then this fourth term, which is a bit of a strange term, but one we'll talk about a lot this semester, and that is the entropy generation term. Now notice there isn't a generation term with either mass or energy. Mass and energy are both conserved. Energy and mass cannot be created nor destroyed. The same is not true for entropy. Entropy is not a conserved property. We can create entropy as a system undergoes a process. We cannot destroy entropy. That is the fundamental premise of what is called the second law of thermodynamics. The first law of thermodynamics says that energy is neither created nor destroyed. It's simply a statement of the conservation of energy. The second law of thermodynamics, however, says that entropy cannot be destroyed, but it can be created. And that's what this entropy generation term represents. We're going to talk more about this entropy generation term a lot as the semester goes on. Okay, so we have this general thermodynamic system and we have our governing equations. How do we apply, or how do we fit our windmill system into this thermodynamic construction, this general construction that we have of thermodynamics? Well, let's figure out what's similar and different between our wind turbine system and our general system. Well, the first thing that we recognize is that our wind turbine system has no heat transfer, right? We didn't write any Q dot terms. There's no exchange of thermal energy between the control system and the surroundings. So we can say right away that the Q dot term in our governing equations will be equal to 0. There's no heat transfer. The second element, which may be a little bit more difficult to recognize, but if you think about it, makes sense, and that is that our wind turbine system can be reasonably modeled as what we call steady state. Now, steady state is a very important assumption that we will make a lot this semester, and you'll make a lot when doing simple thermodynamic analysis as you become full-fledged thermodynamicists. Not every process in engineering can or should be modeled as steady state, but a lot of them can be. And when we assume something is steady state, it very nicely simplifies our analysis for us. So what does it mean to say that our system is steady state? Well, it means that all of our d by dt terms of our control system are equal to 0. In general, steady state means something is not changing with time. Things are not changing with time. They're constant with time. So if we say our control system is steady state, that means that the mass of the control system is constant. It's not changing with time. It means that the energy of the control system is constant. It's not changing with time. It means that the entropy of the control system is constant. It's not changing with time. Whenever we make our steady state assumption, these three terms all become 0, which means that these three terms in our equations, our three governing equations, are all equal to 0. So it simplifies our analysis quite a bit. And later on this semester, we'll provide a very brief example of when we have another specialized situation where in fact our control system is not steady state, and these terms on the left-hand side are not equal to 0. It makes for a more complicated analysis and oftentimes more assumptions that we have to make. Okay, but let's think about this a little bit more, right? So I'm just sort of collectively saying that this is a steady state system, and you may be still scratching your head wondering, well, how do I know it's reasonable to make this assumption that it's steady state? Well, let's think about it for just a minute. Suppose the wind is blowing and it's 20 miles per hour, and this wind is blowing in a fairly uniform direction, right? The wind is coming out of the west at 20 miles per hour. And with, some reasonable acceptance of small changes in wind direction or small fluctuations in wind speed, you can reasonably assume that that wind is coming out of the west going 20 miles per hour. And so because that wind speed is roughly constant and the wind direction or the velocity, if you take the two together, is reasonably constant, it means that the kinetic energy into the windmill system will be reasonably constant, right? In other words, you're going to be transferring kinetic energy to your windmill at a fairly constant rate. Well, if you're supplying a constant flow of kinetic energy to your windmill, and if you've designed your windmill well enough such that, it's got nice smooth operation as it spins in its bearings, well, then you can reasonably assume that the shaft speed is going to have a constant revolutions per minute, right? The rotational speed of the blades in the shaft will be fairly constant with time. In other words, it's a constant rotational velocity. Well, if that's constant with time, then it's reasonable to assume that the generator is going to produce roughly the same amount of electrical power at any moment in time, right? If your shaft power into the generator is roughly constant, then the electrical power coming out of the generator should be roughly constant. So because all of these things are constant with time, and they're all running smoothly and steady, right? And that's where why that word fits in here, then it's reasonable to assume that it's a steady state operation or a steady state process. Okay? And again, our goal a lot of times as engineers is to find ways that we can simplify our analysis, and by assuming something is steady state is one such way to do that. So when we say it's steady state, all our d by dt terms equals 0, right? So now we can go through and see what all of our governing equations will look like. And of course, we have our conservation of mass equation, and because of the steady state assumption, this dm by dt term is equal to 0, right? But we still have the right-hand side of mass flow in minus mass flow out, but now mass flow in minus mass flow out equals 0, and so we can say that our mass flow in is exactly equal to our mass flow out because of the steady state assumption. Likewise, if we now look at our conservation of energy and we think about the two approximations that we're making, well, first of all, on the left-hand side, dE by dt is equal to 0 because of the steady state assumption, right? The energy of the control system is not changing with time. And because there are no heat transfer terms in our windmill system, our Q dot term is equal to 0. Right? There is no heat transfer. That's a special situation or a special process that we call adiabatic. Whenever you hear or see that word adiabatic, it necessarily means that the Q dot term, or the Q term if things aren't on a rate basis, in other words, there is no dot, are all equal to 0. Of course, we didn't make any statement about our work transfer term. In fact, we had that drawn out on our windmill system, our thermodynamic representation, our control system. So this term is likely non-zero. We have kinetic energy into our system, so the E dot in term is non-zero. And we have kinetic energy out of the system, so our E dot out term is non-zero. Now, we could also go through our second law, or our entropy equation, but we're not going to do that simply to save time in this auxiliary lecture, largely because there isn't a whole lot of meaningfulness that second law equation will tell us just yet in terms of our windmill analysis. But we'll be using that entropy equation numerous times this semester. Okay, so if we further process our conservation of energy equation, of course, we have 0 on the left-hand side because our dE by dt term is equal to 0. And on the right-hand side, we just have negative W dot plus the sum of our energy flow in terms minus the sum of our energy flow out terms. And just algebraically refashioning this gives us that this W dot is equal to our E dot in minus E dot out. And so I put a box around this equation because this really is our governing equation for our control system of the windmill. Now we need to provide a little more definition on this E dot in and E dot out term. And remember that this E dot is a collection of three major terms of the flows in and out of a control system. So for our purposes, this energy flow rate into our control system starts with our mass flow rate, okay? So we have the mass flow rate of the air into the control system. And then we have these three elements of energy that are flow in or out of our control system, since it's the same formulation for the out equation. There's three terms that this energy comprises. The first is what is the basic energy of that fluid itself. And in the case of a flow that's crossing a control surface, that energy is what we call the enthalpy, okay, which we represent with the letter H. So this Hn represents the enthalpy of the wind entering the control system. We also have the kinetic energy, which of course is 1/2 v squared, and then also the potential energy, which is the gravitational constant acceleration due to gravity times the potential elevation of that inlet flow. And we get the same thing for the energy flow out term, mass flow out times the enthalpy of the flow out, plus the kinetic energy of the flow out, plus the potential energy of the flow out. So if we include these definitions for our energy in and energy out rate terms, then our W dot equation, so this equation up here, I'm just filling in the details about E dot in and E dot out down here. And so substituting E dot in, we have M dot in times the enthalpy in plus the kinetic energy in plus the potential energy in minus our E dot out terms. So our E dot out, M dot out times the enthalpy out plus the kinetic energy out plus the potential energy out. Okay, so now let's take a look at this. We have an M dot in and an M dot out, and we can rationalize that these two are exactly the same because there's one mass flow in and there's one mass flow out. And from conservation of mass, we see that our M dot in is equal to our M dot out. So rather than carrying around this in and this out with our equation, I'm just going to drop them because they're the same term, the same value, and just call this M dot, our mass flow rate in and out of the control system. And when I make that substitution, we now get this algebraic simplification for our W dot term. Okay, so I'm just separating the fact or combining the fact that M dot in is equal to M dot out and replacing it with M dot. Okay. But now I need to provide a little more information on what this M dot, this mass flow rate, is. Okay, so mass flow rate, M dot, is essentially, the one way to think about it is to think of it as a volume flow rate of the wind, or V dot, times the density of that wind, or the density of the air. So that's what I've written right here. The mass flow rate of the air is the density of the air times the volume flow rate of the air. And of course, as I've mentioned in class already, we don't usually talk about things on a per volume basis, right? Note that density is mass per volume. We always talk about things in thermodynamics on a per mass basis. So rather than write this as density, it's better to write it as what we call the specific volume, which is just the inverse of density. So rho is equal to 1 over this little v, which is actually mu, the Greek letter mu, okay? And this Greek letter mu is what we call the specific volume, or the volume divided by the mass. So it would have units of cubic meter per kilogram, for example. Okay, well, if we think about volume flow rate a little bit further, that's actually something that we can measure directly. But it's actually a little bit easier to measure wind velocity and to calculate the flow area, right? So if I just scroll up here very quickly, talk about flow area just one quick moment, right? Remember that we talked about this wind tunnel, and the inlet to the wind tunnel is defined by this diameter, which is basically established by the diameter of the blades, okay? Well, I'm just giving you the, basically the two-dimensional representation here, right? We have a dimension in the y direction and we have a dimension in the x direction with the flow of the wind. Well, if you now position yourself right here and you look into the center line of this blade, of course, or the center line of this rotating shaft, of course, you'll realize that these rotating blades are in fact sweeping out of an area. And the diameter of that area is, of course, the diameter of the blades, right? So this blade diameter essentially is the characteristic measurement of what is called the effective flow area, right? And the flow area is basically the two-dimension representation of the flow in the up and down direction, as well as the direction going in and out of the page, which of course I can't show you, right? It's just that third dimension that's not being represented on this sheet of paper because it's going in and out of the paper, okay? So that's basically our effective flow area. So returning here to this idea of the volumetric flow rate, right? It's the velocity, which is easy to measure, times the flow area, right, which is easy to calculate since we can measure the blade diameter pretty effectively. So if I combine these, and real quickly before I move on from this, if you're looking at this and you're thinking, well, geez, I never would have combined volume or velocity and area and realized that was volumetric flow rate. And that's okay. One way to think about doing that is thinking about things in terms of units, right? So if you think about your velocity, that you know has units of length per second, okay? And of course your area has units of length squared. Well, if I multiply length per second times length squared, that gives me length cubed per second. And of course volume has units of length cubed, and volume flow rate would have units of length cubed per second. So just by virtue of relying heavily on units, you recognize that velocity times area gives you units that are consistent with volumetric flow rate. And when units are consistent with something, then it's a pretty good bet that it's the same concept. It's the same thing, right? So by virtue of getting length cubed per second with your unit analysis on the right-hand side is a pretty good bet that that means that's what volumetric flow rate is. So if I combine now, my representation of volumetric flow rate into my mass flow rate equation, then I get that the mass flow rate is equal to the velocity times the flow area divided by the specific volume of that wind. Okay, let's think about some of these other terms that we have in our power equation, right? So we have mass flow rate, we've digested that, and we understand that now. We also have the enthalpy in and out terms, we have the kinetic energy in and out terms, and we have the potential energy in and out terms. So let's go through each of these terms and see if we can rationalize how we analyze them since we want to be able to calculate the power of this windmill system. So if we look at enthalpy in and enthalpy out, well, basically the one thing that we need to know is that in the case of something like air, and we haven't precisely learned this in class yet, but we will when we talk about properties, particularly properties of ideal gases, what we'll learn is that the energy of an ideal gas, and enthalpy is basically representing the energy of the air in this case. The energy of an ideal gas is primarily a function of temperature, okay? Air is very nicely, almost always, modeled as an ideal gas. So what that means is that the enthalpy of the air is a function of the temperature of the air. So enthalpy in and enthalpy out really depend on the temperature of the air and nothing else. It doesn't depend on the kinetic energy, it doesn't depend on the potential energy, it doesn't depend on the pressure of the air. Because air is represented as an ideal gas, we can say that the enthalpy of the air is only a function of temperature. Well, let's think about what the temperature of the air is doing through our control system. We have wind blowing in and we have wind blowing out. And that wind is blowing across these blades, and these blades are at the same temperature as the air itself. So there's really no reason to believe that there's a substantial change in the temperature of the air as it flows through our control system, as it flows through the wind turbine system. So we can basically assume that the temperature of the air stays constant as it flows through the wind turbine system. Because enthalpy of the air is primarily a function of the temperature of the air, since the temperature of the air isn't changing, the enthalpy of the air is not changing. In other words, the enthalpy of the air into the control system is about the same as the enthalpy of the air out of the control system. Because these two terms negate each other, right, H in minus H out, we'll be able to cancel these two terms from our first law formulation. Okay, what about the velocity terms, the kinetic energy terms? Well, we have velocity in and we have velocity out. So the velocity of the wind in, this of course is non-zero, so we can't neglect that. And likewise, the velocity of the wind out of the control system is also non-zero, so we cannot neglect that either. So these two terms have to stay in our equation. What about potential energy though? Well, so of course this GZ in and this GZ out, these represent potential energy in and potential energy out terms. And again, usually, right, think about what's going on here. The wind flows into the control system at a certain elevation, and that wind doesn't change elevation substantially as it flows through the wind turbine system. In fact, it probably doesn't change elevation at all. So the potential energy of the wind is basically the same, right? The potential energy of the wind going into the control system is the same as the potential energy of the wind exiting the control system. So we can reasonably say that Gz in, the potential energy of the wind in, is equal to Gz out, the potential energy of the wind out. And because they're the same, and like enthalpy, because they negate each other, these two terms, Gz in and Gz out, will also cancel out by virtue of them being the same, and this minus sign that's here in our first law equation. Okay, so putting all this together now, we have our W dot equation, right, which is equal to the mass flow rate times enthalpy in plus kinetic energy in plus potential energy in minus enthalpy out plus kinetic energy out plus potential energy out. Well, we can cancel H in and H out because these two terms are basically the same. And we can cancel Gz in and Gz out because these two terms are basically the same. So what does that leave us with our first law equation? Well, it tells us that the power that's produced by our control system is equal to the change in kinetic energy of the wind through that control system. In other words, 1/2 times the mass flow rate times the change in the kinetic energy in minus, times the velocity squared in minus the velocity squared out. And we have a relationship for mass flow rate in terms of velocity, area, and specific volume. And so we can substitute that in and get that our power in is equal to 1/2 times the velocity in times the area in divided by the specific volume in times the square of the change in velocities through the control system. Now we're gonna process this a little bit more, but before I do that, I just want to stop and take a conceptual break on what this equation is telling us. And if you think about this conceptually, this equation will make a lot of conceptual sense for you. Let's go back up to our general representation of our wind turbine system, right? And we basically said that the electrical power from the control system was equal to the energy into the control system minus the energy out of the control system. In other words, the change in kinetic energy of the wind, that would be this E dot out minus E dot in, is equal to the electrical power that leaves the control system. That makes sense. That's conservation of energy. Energy must be conserved. And because we're representing our system as operating as steady state, none of the energy is being conserved none of the energy is being stored in our control system, or there's no stored energy in our control system that's being additionally released during this process. In other words, the change in energy between these two terms must equal this energy flow out that we have here represented as W dot electric. And that's exactly what our mathematical equation is telling us. It's telling us that the power of the control system, the power leaving the control system, this W dot, is equal to the difference in the kinetic energy between the inlet kinetic energy and the outlet kinetic energy. Okay, so I mentioned that we would process this equation a little bit further. And in fact, what we really need to do is we need to dissect what we do about this inlet area and this inlet specific volume. So in the case of our inlet area, right, well, you know that, assuming a circular cross-sectional area, which is a good assumption to make considering that the blades sweep out a circle, that inlet area is just pi r squared, right, where r, the radius of that circle, is basically the radius of the blades. Well, we were provided with the diameter of the blades, so we can just make the substitution where diameter is r divided by 2, or diameter is 2 times r, and so when we do that, we get that the inlet area is pi over 4 times the diameter of the blades squared. Okay, no problems there. Okay, now what to do about this specific volume? This is a little trickier, right? Now, sometimes the specific volume or the density will be given to you directly, right? So if you're given density directly, then, and you know that the specific volume is just the inverse of density, so you can very easily calculate the specific volume if you're directly given the density. But what if you're not given the density? Well, in that case, you can estimate what your specific volume is using the ideal gas law in this case. And again, air is what we would call our working substance or our working fluid. That term will come up more as the semester goes on. And air can almost always be modeled as an ideal gas. I say almost always because you may find some niche application where air is starting to become what we would say a real gas as opposed to an ideal gas. But for the purposes of our discussions of air this semester, you can always model it as an ideal gas. So of course the ideal gas equation, we're gonna formulate this more later on this semester because this probably isn't necessarily the form that you've seen from your chemistry classes. But the specific volume of an ideal gas is related to its gas constant, R, times its temperature divided by its pressure. Okay? So again, if you haven't seen the ideal gas law written precisely like this, don't worry. We'll go over this again later on in the semester. One quick caution that I want to make, though, is this R value, this R parameter that's listed here, this is not the same as the universal gas constant, right? So this R is not what I'll call R bar, where R bar represents the universal gas constant, which of course you're probably familiar as being equal to 8.314 kilojoules per kilogram Kelvin. Instead, this R represents what is called the gas-specific constant. That is, the value is specific to the gas that we're studying in the system. And again, we'll talk more about this later on, but for now, what you need to know is that the gas constant for air is equal to 0.287 kilojoules per kilogram Kelvin in the metric system, and it equals something else, of course, in the British system, and you can look that up in your table A1E in the back of your textbook. Okay, so now we can reflect on this W dot equation, and now basically we have knowledge or a way to determine each one of these parameters. So if we wanted to calculate the power from a windmill system, we would just use this equation. Okay, easy peasy, no major problems there. And you know how we developed this equation, starting with our conceptual representation of our thermodynamic system, using our governing equations, and simplifying by applying appropriate assumptions. Okay, so the final question that we may ask ourselves is how do we quantify the efficiency of this windmill system, right? Remember I said in class that anytime we convert energy from one form to another form, we can define an efficiency. And in general, that definition of efficiency is conceptually defined as what we get divided by what we pay for. So what is it that we're getting in the case of a windmill, and what is it that we're paying for? Well, what we get is W dot, the electrical work energy, or power, since it's written as a rate term here. What do we pay for? Well, it's kind of weird to think of this because a lot of times we'll associate this word pay with an economic pay, right? In other words, what do I physically have to hand over some dollar for, some coinage? But thermodynamically, when we say pay, what we mean is where are we getting the energy from? What's our energy? Even if we don't pay someone for it, even if there's not a transfer of money to get that energy, we're still getting the energy from something, and therefore, in quotes, we're paying for it in some way. Well, what we're paying for in the case of a windmill is in fact the kinetic energy of the wind entering our control system. Okay, so this E dot N represents what we pay for. So the way we define the efficiency of a windmill system is the electrical power out of that windmill divided by the inlet kinetic energy into that windmill. Okay, well that's it. Hopefully now you know everything that you've ever wanted to know about windmills, or at least how to analyze them thermodynamically. If you have any questions about this auxiliary lecture, just feel free to send me an email or stop by my office. Thanks very much for your attention. Have a good day.